All right, now we know that we need to encrypt some strings before storing them, so let's find out how to do that. And I did a little digging around and I found this resource online which actually looked pretty good. So you can go ahead and read through this if you want to. It's about encrypting strings in Android. Let's make better mistakes. A provocative title. But for purposes of this video, we're going to skip down to a Java class that can help. And there's a project on GitHub. And what we need, we don't need the entire project. What we need is this AES CBC with integrity. And AES is the American Encryption Standard. And this particular code base uses 128-bit AES, which is considered pretty good. And then CBC is cipher block chaining, which is basically applies to encoding blocks of data. There are also streaming protocols and some other block chaining protocols, but this one's okay. And then there's also this myactivity.java file, which has an example of how to use this code. So I'm going to click on this link and go to raw. So here's the actual code for the class. And I'm going to select all and copy. And then I'm going to go to my crypto code and right-click on com.example.mark.crypto, create a new Java class, and I will call this crypto. So it gets com.example.mark.crypto is the package name. And then I'm going to replace everything else with the code that I just grabbed. And everything is red because I have two package lines. So I have my original package line and now I have that. So I'm going to get rid of this package line. And I think everything is good. Let's go ahead and build it. Okay, so the class here is named AES CBC with integrity, and we want to change the class name to crypto. So now that matches. So now we have a crypto class that has the AES CBC with integrity stuff in it. And let's just take a quick scan through here. I'm not going to spend a huge amount of time on it. But basically, the concept is that you have a plain text, which is the regular text that you can see and you want to use. And somehow you want to convert that plain text into a ciphertext. So the ciphertext is the encrypted version of the plain text. And then this should be a reversible operation. So you should be able to take the ciphertext and decrypt it back into a plain text to recover the plain text. Now, to do that encryption, you need a key. So a key is a set of data that's used to convert a plain text into a ciphertext or a ciphertext back into a plain text. And then in order to generate the key, well, you need a password and you need a salt. So secret keys manages generating the keys class, so secret keys. And then there's a generate key method that returns a random key, or there's generate key from password, and this is the one we're going to be using. So this one takes a password, which is supplied by the user, and it also takes a salt. So salt is a set of random values that's safe to save. So the idea behind a salt is if you just give me a password and I use that to generate my key, I have some issues here because the password that the user chose might not be very strong. And also, there's a common attack against cipher systems where basically someone offline ahead of time generates every possible password up to a certain length using a certain character set, and then stores the results of hashing those values in a table. And then at runtime, they can take a ciphertext and generate a hash code or extract a hash code from that and use that to look up the password in the table. So it's possible that somebody has already pre-computed some values on this password that can be used to defeat the encryption if they get access to the ciphertext. By adding a salt, which is a set of random values, it makes it unlikely or impossible that someone will have pre-computed the hash based on both the password and the salt together. So it's an easy defeat for a very common attack by including a salt. Now, the idea behind the salt is I'm going to generate a set of random values. I'm going to store the salt so that I can use it later to decrypt the text. But then every time I re-encrypt the text, I can generate a new set of salt values. And if I keep the password completely secure by never storing it anywhere where anybody could get a hold of it, then basically the whole system is going to be secure. So salt gets stored, password doesn't get stored, and then I use the password plus the salt to generate the key, which is then used to encrypt or decrypt the message. Now here's the main encryption method. So this is going to take a plain text and it's going to take a set of keys, and it's going to return the ciphertext IV MAC. So ciphertext I've already explained, it's the encrypted text. But then it also includes some random initialization values. So every time you encrypt a piece of text, you should generate a new set of random encryption values, random initialization values, and then that gets stored along with the ciphertext as well. And then MAC is message authentication code. So this is basically a fingerprint or a signature that is associated with the message so that you can tell whether it's been decrypted properly, and we'll take advantage of that when we start decrypting. So there are some other methods that have to deal with encrypting a block of bytes rather than a string. And then later on we'll see there's a whole bunch of stuff having to do with this PRNG. So a PRNG is a pseudo-random number generator. So when you call a random function, it gives you a random number, and then that's going to serve as the basis for encryption and decryption. And it's pseudo because if you start with the same seed, the same initial values in the random number generator, you're going to get exactly the same sequence of pseudo-random numbers. But unfortunately, the pseudo-random number generator that's built into standard Android libraries isn't particularly useful for encryption because it has, once again, some well-known predictabilities and some irregularities. A good pseudo-random number generator is going to have basically equal chance of returning any byte in the range. The random number generator that's built into the Android libraries has a little bias in it. It's like if I'm using a set of loaded dice and they keep coming up sixes more frequently than they should. It may not be enough for a person to notice that sixes are coming up a little more frequently, but over a long period of time, that bias can help somebody make money rolling dice. So this is the same kind of thing. The random number generator that's built into Android is pretty good, but it's not really suitable for strong encryption. So we have some fixes to the pseudo-random number generator. And then we also have this decrypt string, which takes the ciphertext IV MAC, takes secret keys, and is going to recover the plain text from that. Then there's a version for 4 bytes instead, and generating a message authentication code, the subclass for secret keys, and this is an interesting little bit here, this constant time comparison that takes 2 vectors of bytes. So if you want to compare 2 strings to see if they're equal or not, you can start at the first character, and if it doesn't match, then you exit. If it does match, you look at the second character. If that doesn't match, you exit. If it matches, you look at the third character, and so on. And that's how most string comparison happens, because it's as efficient as you can possibly get. But that's bad for cryptology, because if you're comparing 2 passwords, for example, and you want to see whether they match or not, if they match on the first character but mismatch on the second character, it's going to finish pretty quickly. If they match on the first 20 characters and mismatch on the 21st character, that's going to take a little longer. And if it matches for the first 40 characters, that's going to take a little longer, and so on. And that difference in time to do the string comparison has actually served as the basis for some exploits that were used to defeat encryption. So one way of removing that source of information to somebody who's trying to crack your password is by always using a constant time equality test. So this function basically does the same thing as a regular string compare does, except it's always going to take the same amount of time to run, whether the strings match or not. Then here's where the ciphertext IV class is defined and some helper methods for that. Here are the fixes to the pseudo-random number generator, and there's a lot of this stuff. So a lot of stuff for the pseudo-random number generator. And that's pretty much it. So that's what we got in our security class. Now let's go ahead and try using it. So I'm going to start with a really simple example. Hopefully it will be really simple. And let's create a plain text. And now we want to encrypt this plain text. So we need two things. We need a password and a salt. But I'm not going to specify the salt string. I'm going to let the system generate one for me. I'm going to store it in string form because I'm going to ultimately want to put it in my bundle, in my shared preferences later on. And so I want a salt string, which is going to be crypto dot generate salt and crypto dot salt string. So I'm getting a little red squiggly under here because this thing can throw an error, throw an exception. If I try to use a security method that isn't implemented in the library, it's going to throw a security exception. So I have to wrap this whole thing in try catch to catch that exception. And now I have a salt string. Now you'll notice I have to say crypto all over the place. If I get rid of the crypto and Alt plus Enter static import and do the same thing here, Alt plus Enter static import. So I can keep doing that. So now I have a salt and a password. Now let's create some secret keys from com.example.mark.crypto. So there's my secret keys equal generate key from password, and I'm going to pass in the password and the salt string. So now I have some keys. Now I want to encrypt my text. So this is going to be a CIV ciphertext IV MAC ciphertext is equal to encrypt, and I'm going to give it my plain text and my keys. So this one also throws an exception, so I'm going to add a catch clause. So now I could get general security exception from some of these calls and unsupported encoding exception from some of these calls. So now I should have a ciphertext, so let's go ahead and log it. And I'm going to go ahead and add a log tag. And here I'm going to log.d log tag ciphertext plus, and then ciphertext, this is a complex binary object, and I want to convert it to a string so I can see it. So that's my my encryption side. Now to decrypt it, I'm going to start from the ciphertext in text form, and the password in text form, and the salt in text form. and then I'm going to completely recover my my plain text. So here's the ciphertext in text form. And then, so I'm going to start by regenerating the keys. And I have the password text, and I have the salt text. And then I want to recover my binary ciphertext. And the way I do that is I just create a new crypto.ciphertext, and I pass it in my CIV string. And now I can decrypt it to get a new plain text. And I'm going to give it my new ciphertext. And I need the new secret keys. And there's an optional encoding, which I won't worry about. So at this point I should have my plain text as well, so let's go ahead and log that. And if this works correctly, I should have this as an example plain text in my log. So let's go ahead and try it. Run it on the Genymotion. And let's see what we got. Yeah, so I got my plain text back. Here's my ciphertext. Let's just look at the main activity stuff here. So our ciphertext is this complicated thing, and this is all that anybody who manages to get root access to our phone is going to see. But we can recover it using the salt and the password.